In order to build production value electronics, we have to understand it. This is the part 2 of a longer series where I go into fundamental concepts of electronics, and today we're going to look into the basic schematic of an ACDC switch mode power supply. Let's get to it. So first we see an AC voltage source, a bridge rectifier, a capacitor, an RCD clamp circuit, which I won't go into detail on in this video, I'll leave that for another video, then a transformer, a output diode, a output capacitor, and a load. Down here we have some leak inductance, drain to source capacitance, which I will only touch upon briefly. And then we have the MOSFET. And lastly, we have the controller. So what happens here in order to get, for example, between 80 to 265 VAC over to, let's say, 12 volt DC. In order to do that, we use this circuit and we use its components in order to do that. So last video I looked through the stages of an ACDC switch mode power supply, and right now we'll look into what components performs each task. So the AC mains will enter this bridge rectifier, and what we will see on the output is a pulsed DC signal. This bridge rectifier performs full wave rectification, which means that it essentially chops off the negative portion of the AC signal and flips it over so that you have a pulsed signal, like so. So the AC mains enter this bridge rectifier and it turns the AC signal into a pulsed DC. And what happens is this capacitor will charge up at the peaks and it will release its stored energy below the peaks. It charges at the rectified peak and it supplies energy between the peaks. So it will store and then it will release, which means we have a very high voltage stable DC signal. Then this high voltage DC here will be chopped at high frequencies due to this MOSFET before flowing in to the transformer. This transformer provides isolation and a step up or a step down ratio based on this based on the windings of the transformer. So you have a ratio here saying in order to go from 80 to 265 AC voltage to 12 volt DC, you need to construct or at least select the appropriate transformer in order to get that type of ratio. So NP is the ratio, is the number of windings for the primary coil, for the primary side, and NS is the number of windings at the secondary side. Now this transformer is not ideal, so what you have is some leak inductance and some drain to source capacitance. Some flux will not be transferred from the primary side over to the secondary side, and that forms something that is called leak inductance. So when the MOSFET is turned off, this energy has nowhere else to go, which results in a very high voltage spike at the MOSFET drain terminal. The MOSFET also has its own parasitic capacitance called drain to source capacitance, which interacts with the leak inductance, which can cause ringing at the turnoff. And that's where this RCD clamp circuit comes in. So this energy, it has to go somewhere in order to protect our MOSFET, and we implement an RCD clamp circuit, which essentially takes the energy and finds a way to store it and dissipate it in the form of heat. So you have this circuit is made up of a resistor, capacitor, and a diode, which I won't go into detail in this video, but I will save that for a different video. The controller IC is just a pulse width modulation signal which controls this MOSFET based on the design prerequisites. So again, here we have a high frequency DC signal which is transferred over to the secondary side. So the secondary side receives this high frequency DC voltage, but due to the turns ratio, we have a lower voltage. The current flows through the diode, which again rectifies the signal and removes the AC component. Again, the capacitor stores the energy at the peaks and releases it between the peaks. Thank you for watching this video on an ACDC switch mode power supply circuit. In the future, we'll look into more elements of this circuit and also how to properly size and select components for your application. Thank you for watching. This is Velta Potential, and until next time, ciao.